Okay, so modern industrial agriculture, it's basically a massive high-wire act. Every single day, we're out here trying to maximize crop yields just to feed the world, all while desperately trying not to totally destroy our topsoil and water ecosystems. It's precarious, to say the least. But there's a recent breakthrough out of Louisiana that has agronomists and climate scientists everywhere doing a massive double take. In this explainer, we're going to unpack exactly what happened when researchers decided to take agricultural waste and shove it right back into the ground. 22%. Just let that sink in for a second. That is a massive spike in initial plant cane harvests. Okay, let's dive into this, because honestly, this isn't some minor incremental tweak. No way. This is a staggering yield spike headline that completely changes the math of modern farming. But to really grasp how they pulled this off, we've got to look at what they actually put into the dirt. So the secret ingredient here is something called sugarcane bagasse. When sugarcane gets processed, the juice is extracted, right? And what's left over is this crushed, fibrous, stocky material. Traditionally, this stuff is a massive headache. It just gets stockpiled, or worse, burned for really terrible low-efficiency industrial heat, which just pumps carbon straight up into the atmosphere. But researchers at Louisiana State University, or LSU, they took this exact waste product and turned it into an overall average crop boost of around 15% across their tested acreages. Section 1. The science of pyrolysis. All right, before we get completely swept up in the hype of those giant numbers, we really need to demystify the chemistry here. Because you can't just toss raw, crushed stalks out onto a field and expect a miracle. It has to undergo a very specific transformation called pyrolysis. Now, simply put, this is the high-temperature thermal decomposition of organic material under oxygen-limited conditions. And we need to be super clear on this point. This is not your standard furnace charcoal, and it's definitely not the briquettes you're tossing in your backyard grill. What pyrolysis creates is a highly recalcitrant carbon lattice. It is a completely different beast. So let's walk through this physical transformation together. First, you take that raw waste. Second, you hit it with that intense oxygen-limited heating. During this step, all those volatile organic compounds just completely cook off and escape. And what you're left with in step 3 is this exceptionally porous carbon lattice. Imagine a microscopic honeycomb structure. By baking it this way, you massively increase the surface area of the material. What's really fascinating, though, is how that honeycomb actually behaves once it's in the ground. Think of this biochar as an ion sponge. In a super humid, subtropical climate like Louisiana, heavy rainfall is constantly washing your expensive synthetic nitrogen and phosphorus fertilizers right out of the root zone. It's a huge problem. But when you amend the soil with this highly porous biochar, it traps the moisture, it acts like a magnet, immobilizing those synthetic fertilizers and holding onto them tightly before those heavy rains can just wash them all away. And this ion sponge effect is so incredibly powerful that it actually shifts the fundamental dynamics of the soil. By locking on to those nitrogen fertilizers, the biochar drops the net carbon to nitrogen ratio by up to 19% compared to untreated plots. In plain English, it keeps the plant food exactly where the roots actually need it, instead of just letting it wash down the drain. You know, this brilliantly illustrates a fascinating connection between 21st century material science and ancient ecological intuition. We actually call this the Terra Preta parallel. Terra Preta translates to dark earth. And long before modern chemistry came along, pre-Columbian indigenous populations down in the Amazon were enriching their naturally nutrient-poor soils using charcoal, bone, and organic waste. Because biochar carbon has this incredibly high chemical stability, it stays trapped in the topsoil for centuries without breaking down. We are quite literally, right now, rediscovering an ancient technology. Section 2. Nuance and scientific skepticism. Now, as enthusiastic as we are about this, it is time for a bit of a reality check. We have to look at the specific data coming out of the LSU Sugar Research Station in St. Gabriel, Louisiana, and, apply some rigorous scientific skepticism here. When researchers applied 11 megagrams of fresh biochar per hectare, the results were actually highly variable, and it all came down to the physical texture of the soil itself. In light-textured soils, boom, they saw that incredible 22% immediate yield increase. But in heavy-textured soils, the yield spike was only 12%. So the physical structure of the earth you're working with absolutely dictates how effective your sponge is going to be. However, we gotta remember, it's not just about the raw harvest tonnage. Take a look at these environmental defense metrics. By trapping all those nutrients, the biochar significantly reduces cumulative runoff volume. It drastically lowers nitrate and phosphate leaching, and it drops the amount of suspended solids in the water. This is absolutely crucial, because it means we're actively preventing agricultural runoff pollution and stopping stream eutrophication. That's where water bodies get overly enriched with minerals and nutrients, which just completely chokes out the aquatic life. So, seeing those crazy yield spikes and the massive environmental benefits, we have to ask the critical question, right? Is biochar just a universal magic bullet for modern agriculture? Because when you read these sensational agronomic headlines, it is so easy to think, wow, we've done it. We've solved the global food crisis. No.
Exactly. No, we absolutely cannot treat this as some quick, universal fix. Real, long-term agronomics requires objective, sober analysis.
Let's just rapid fire through some of the bottlenecks to mainstream adoption here, courtesy of subsequent field trials by the USDA. First up, application rates matter immensely. If you use less, you might technically increase your soil carbon, but you're going to see zero short-term harvest boost. Second, the efficacy is highly dependent on your baseline soil texture, the microbial ecology, and the pH. Third, it relies heavily on your regional climate. And finally, the economic feasibility. The sheer high cost of industrial-scale pyrolysis, the transport, the land application, it's a massive hurdle. This is a highly context-dependent fix, guys. It is not a cheat code for farmers. Section 3, revolutionary or overhyped fix. Which really brings us to the bigger picture. This whole experiment represents the transformation of waste into value through these amazing ecological feedback loops.
Right, and just think about the historical legacy of sugarcane for a second. This is a crop that is deeply tied to colonial expansion, monoculture, and just severe soil depletion. But taking those spent husks, turning them into a charred skeleton, and returning them directly to the ground, we're actually attempting to move agriculture away from this cycle of linear extraction and toward a truly restorative closed loop.
It's a profound shift in human stewardship. But I want to leave you with a final thought to ponder long after this explainer ends. By using advanced thermal technology to forcefully inject this carbon back into the earth, are we truly mimicking natural metabolic cycles to create a sustainable circular economy? Or are we simply deploying an incredibly expensive technological intervention just to delay systemic ecological exhaustion?